Hi everyone, welcome to my YouTube channel. In this playlist, I will be going through some of the technical topics based on my past work experience. And in this specific video, I will be discussing on Fourier Transform. Oh wait, let's make it discrete Fourier Transform because in this video we will be dealing with some discrete data, for example. So DFT would be nice place to start with. I will not be going in detail about DFT, FFT, or the speed of different algorithms. The main intention of having this video recorded is to see mathematically how interesting this transformation is, and this is my perspective of DFT. Different people have different opinion and their own perspective. And one more thing is, in case if I feel like there are some prerequisites required while going through this lecture, I will keep on listing it on the right hand side of the screen. So all you need to do is, in order to get familiar with those topics, in case if you are not aware of it, just watch some other YouTube videos and go through the internet. So before we start on the Fourier transformation, I would like you all to see how the Fourier transform of a simple function looks like. And here we have an image, and let's see first transformation. On the left hand side we have a cosine harmonic wave function, which is a function of time, and on the right hand side we have only one data, which is nothing but highlighting an arrow towards upwards, which is a function of omega. Since the harmonic function on the left hand side has only one frequency component, after doing the Fourier transformation we are getting only one data point, because as I mentioned earlier, it has only one frequency component. Now in this specific lecture, I will not be going through, or I will not be discussing anything at all about the independent variables, time or frequency, because if we look at the DFT page, which if you see at the formula, it has no mention of independent variable being time or space. It can be used for any data, because while doing the transformation, all we need to input is a vector, which is usually a dependent variable, and later we will map the independent variable. That we will be looking another video. So let's go back to our workbook. Before we start, I have an important statement to make. Do not say Fourier transform, it would be FFT, DFT, or anything, is used for time to frequency conversion. Please, no, do not say double, triple. This is very, do not say something like this, especially in front of any professor, at least. I mentioned it earlier, your data could be a function of time, space, or maybe, I don't know, any other variable. And if you go through the Wikipedia page on the Fourier transform, it has no mention of the independent variable in the formula itself. Yes, it does mention in the wiki page, but that is not how one should define the Fourier transform. So this is a very important point to remember. Do not say Fourier transform is used for time to frequency. Yes, it does if the provided data is time dependent data, but what if I give you spatial data? So it is really a very narrow-minded answer if you say it is used for time to frequency. So if that is clear, let's see how the mathematical transformation works. So based on Wikipedia, this is what I got. Let's segregate into three parts. This is 1, this is 2, this is 3. There are 3 terms. So what are these 3 terms? Capital Xk is my output vector. This is what I want after the transformation. This is what the result is. Capital small x is my input. This is what I am supplying to get the desired output. Input. Now we have the small subscripts, small k, small n. These are the iterating variables to carry out the summation. So both of them starts from 0, but 0 to 40. So as you can see, this will define my maximum or till what range it would carry out the summation. So that would be n minus 1. So since we are starting from 0 to n minus 1, my total number of data is n. And that is what capital N stands for. N is my number of input data points, and it is same as my output data points. So just to give you an example, if xn is something like x1, x2, x3, it goes to xn, even my output would be of the same size. If it is of size 10, it will be of size 10. If that is clear, we are done with kn. So we are done with the variable defining. So in this transformation, what I am doing is I am supplying an input vector of some specific size, and I'm getting an output vector of the same size as my input. Now let's see how the transformation works. This is where the actual video starts. Now I said our output data size would be same as input data size, right? So, and if you remember at the start of the video, I showed you the transformation of a cosine function. That is a sine function. to which has only one frequency, and the Fourier transform looks something like this. That's all right at one particular frequency. It was time data. Now if I'm taking my input data size as 50 over here, my output data should also be 50, right, as I said earlier. So if we focus on the left side, since I'm getting the response at only one particular location, it means out of 50 data, 49 are almost zero. That's why it's not showing up in the response, right? Only at one data point I'm getting the response. So this is what we are expecting from the Fourier transformation, that of all the data I will get a response at one particular point, provided my input signal has only one frequency content. So if my input signal has different frequency contents, I will get the similar number of data points in my transform data. But this is what we are expecting. This is not completely true, but we will come to this point at a later stage. But for now, let's assume this is true. And if my input data size is 50 and output data size is 50, and if my input has one frequency content, then my output data will have only one point where the response will shoot up, while for the remaining 49 data points my response will be 0. If my input data has two frequency content, I will get 2 points in the output data where response will shoot up, and remaining 48 points will have 0 amplitudes. So this is the logic we need to build on, how this is mapped from left side to right side. Let's see the mathematical interpretation of this. Before going that, I'm really not comfortable with the exponential term, so we will use something like Euler's identity, which states something like this. Now in our case, theta is nothing but 2 pi k small n by capital N. Now one more thing about this. If you say this, n is going from 0 to n minus 1, and n is a fixed number, so n by n process, it's nothing but we are normalizing it. What it means is, no matter how much data we take for the transformation, this would have this same range no matter what is your data size. So the minimum would be 0 and the maximum would be close to 1 for any case. For example, if my input data has a size of 10, so for n, the lowest is 0, max is 9, it goes from, so n by n goes from 0 to 0.9. It means for a particular problem or for a particular transformation, n by n is fixed, since my capital N is fixed and my iterating variable is fixed. So this normalizing range is also fixed. And this k term over here would determine the something. Let's say we will define it as frequency for now, because this looks same if you compare it with cos omega t. T is nothing but analogous to n by n, and omega is analogous to k, 2 pi k. So k is analogous to frequency. So when we are iterating over the output variable, since k is in the output side, since as k goes from 0, 1, 2, 3, we are changing the frequency content of the harmonic function in the formula. Now I know it was quite a mess up over here, but I'll try to simplify things. Just to simplify things, let's not take the imaginary part for now, and my formula becomes xk is n goes from 0 to n minus 1 xn cos of 2 pi k small n by capital N. And I'm omitting the imaginary part. K iterate from 0, 1, 2, 3 till k. N iterates from 0, 1, 2, 3 till n. Right. So let's try to expand k. So it says my first value of transformed variable x0 is nothing but summation of 0 to n minus 1 xn cos of k is 0. I know it will be k is 0 n by n. So no matter what value of n I take, this term will be always 0. So my x0 will be always a constant. It will be simply summing x0 plus x1 plus x2 till xn minus 1. And similarly we will have imaginary part, but it will be 0. Now x1 is x0 cos of 2 pi k is 1. I will change the color. So xk is 1, so this is 1, and I will use green for n 0 by n. So this will be, then you have x cos 2 pi n plus x cos 2 pi n plus it goes till some value. Now this is where we need to look for. We have here one product, then another product, right? So what is really happening over here? And then we will get a scalar value. Does this look familiar to anything? We have a product, then summation, product, summation, and it will go till the n minus 1. So To recap, let's see orthogonality of vectors. How do we check the orthogonality of two vectors in a Cartesian coordinate system? If I have a vector u, I will simply say if the inner dot product is 0, it's both the vectors are orthogonal to each other. In other words, both are perpendicular, right? Two ways to interpret this. If we go, the dot product is given by u equals sine theta. Since theta is 90, this will be 0. And another way is when two vectors are perpendicular, it cannot be projected on each other. If I try to project u on v, it is not at all possible. It would come as a point. So that's what the 0 value means. Similarly, for nth dimension case, sine and cosine are orthogonal functions. This would be maybe if you are not familiar with the statement what I made just now, you can refer orthogonality of sine and cosine, and you will come across some summation and integral formula which states that the function is continuous 0 to say some period x, sine x, sine mx and sine nx, it's equal to 0 if 1, it's equal to 0 if m is not equal to n and is not equal to 0 if m is equal to n. This you can try to relate to the dot product what I discussed over here, because a dot product of a vector is usually written as u1 v1 plus u2 v2 plus u3 v3. And if you see, this looks, if you try to compare this one with this one, the first term u1 v1, this will be something like u1 and this is v1, u2 v2, u3 v3. So what is exactly happening? We are trying to take the dot products of two functions, not actually dot product. We are trying to check the orthogonality using this transformation formula, but we are not dealing with our three-dimensional vector. We are dealing with sine and cosine functions, and the orthogonality relation, it looks similar but not exactly similar. So if the sine and cosine functions are orthogonal, it would give 0 if the frequency content are different, and if the frequency content is same, it will not be equal to 0. So if you remember, a couple of minutes back I discussed if we have a sine function and if we check the Fourier transform, we are getting the response at a one particular frequency only, right? At a one particular point, and remaining else we are getting 0. So this is because of the orthogonality condition. So what is happening is, when we are iterating over the k variable, which is the output variable, as k goes from 0, 1, 2, 3 till capital N minus 1, the frequency content goes on increasing as the k, as I said, k is analogous to frequency. So as k goes from 0, 1, 2, 3, the frequency content goes on increasing. So what we are doing is x0, x1, x2, x3, xn minus 1. What we are trying to do is, we are trying to check orthogonality condition between our input data and the harmonic function corresponding to k equal to 0. Sorry. In the second case, check orthogonality between input data and harmonic function k equal to 1. Similarly, input data and k equal to 2. It goes on repeating till input data k equal to n minus 1. So what happens is, if the orthogonality condition meets, the value will be 0. If it doesn't meet, it will give some value. Let's call it as a. Now for this harmonic function, this is how the orthogonality is tested. Now if I am supplying an input signal as this, for now I am not at all bothered about the independent variable, it's only this data I am supplying. So what the transformation will try to do is, it will try to check the orthogonality between my input data, means this sine wave, and sine cosine of 2 pi k n by n, this function, where it will keep on changing the frequency for the output vector. So if the orthogonality condition is met, we will get 0, and if it is not met, we will get some value a. So that is what is happening. For most of the part, we will get zeros where orthogonality conditions are meeting, but only at a particular point we will get some value as a, and this is only when m is equal to n. That is what this formula gives, and that is where we will get our natural frequency, not natural frequency, but the frequency of the signal. But since I have not I'm not considering the independent variable for now, let's not focus on the frequency term, but I'm pretty much sure at one point we will not be satisfying the orthogonality check. That's why we will get some value as a, and that's the basis of Fourier transformation. We will be getting a response like this for one frequency wave, because for rest of the points we will be satisfying the orthogonality condition, but only at this point we will not be satisfying the orthogonality check in vector form. Dot product 0, but here dot product is not 0, and so this was the basis of a little bit on the Fourier transformation. I think it will take a couple of more videos to map the independent variable and to get the exact frequency value, and to see some of the interesting stuff related to mirroring of Fourier transform. Why does that occur, and how can we manipulate the Fourier transform formula to filter out the noise from our signal. But I'm not feeling comfortable now because I feel like it was quite a messed up lecture, as it is the first time for me. I'm not sure if I was able to deliver my points clearly or not, and I feel like even my presentation was not good. From next time onwards, I will try to present in a simpler way. I'm just writing down few of the points that you should Google. Summation, expansion, and periodic and harmonic functions. The difference. What is the difference between a periodic and harmonic function? So yeah, that's all from my side for today. In the next lecture, what we will try to do is we will try to map the independent variable, and let's see where it goes. Thank you everyone. Have a good day. Bye.